Thank you, Ray. First of all, of course, for inviting me also to give this webinar here, and thanks for everybody for listening to it. So today I would like to talk about the recent work that we published in Nature about global sea level rise in the early Holocene, revealed from North Sea peats. And as you can see, it was really a collaborative project with a lot of co-authors and a lot of institutes, both from the Netherlands, but also from the UK, University of Sheffield, Leeds, and also Dutch, now German institute called BGR. As Raymond said, I'm from Deltares. It's a Dutch knowledge institute. So we have about 800 people working in two offices in the Netherlands. And we really focus on all kinds of research with respect to the subsurface, groundwater, things like that, safety, flood safety, dike safety, sea level rise, subsidence, those kinds of topics. So yeah, we are an independent knowledge institute. So we are sort of in between universities and a company. So we are a non-profit organization, and we have huge facilities where we can experiment with waves and things like that. And we focus on these five main topics. So it's really focusing on deltas, of course. Also, the name suggests that already. So we want to keep deltas habitable, make the world's population safer from flooding, resilient infrastructure, healthy water and subsurface systems, and energy transition and climate neutrality. So you can imagine that a lot of earth scientists work here as well. So the work that I do for this paper that I present here, it's not that common for Deltares to look into past sea level rise, but of course it is also useful to look into the past to forecast the future. So that is also one of the key messages in our paper, of course. So I will start off with providing a little bit of background to the topic. So why is it important to look into the early Holocene sea level rise? So of course you all know that sea level is rising at present with a rate of about 33 centimeters per century based on satellite data. But this rate of sea level rise is thought to increase in the next decades and certainly in the next century. And this familiar picture from the IPCC shows you that by 2150, over 1 meter of sea level rise most likely will have occurred since 2000. So that's a rate of over 1 meter per century. And I always find this interesting to look into the different components of current day sea level rise, because I think it's quite surprising to some of you maybe that, for instance, 17% of sea level rise is coming from land water storage, which is already quite a substantial part. And in this case, it's not land water storage at all, but it's groundwater extraction and the groundwater eventually ends up in the ocean. A lot is also coming from thermal expansion. So by warming up the ocean, the volume increases. But of course, also a part is coming from the melt of ice sheets. And if we look into the Antarctic ice sheet, for instance, it's only 10% at present, but it's probably the most uncertain one for the future. And therefore, a lot of people focus on Antarctica. And this illustration here is just for my part to show you how much uncertainty there still is into what ice sheets will do in the future. So what you see in the central panel is time, and here the global sea level rise contribution from Antarctica with all kinds of scenarios, depending on ice shelves collapsing or not. But that's not so important here. But you see that there's a wide range from even negative values to about 30 centimeters for the next 80 years. And if we look further into time, you see that there's a spread between 1.5 and 2.5 meters. So even on a time scale of decades, and certainly on a time scale of centuries, it's very hard at present to predict what the ice sheets will do, meaning that we do not have enough insight into this climate sea level relationship. So therefore, it's very wise to look into the past, and then especially to a period that is sort of an analog for today, which is the early Holocene from about 12 to 8,000 years ago. So that's the first period after the last ice age, when large ice sheets started to melt really rapidly, and temperatures were rising about 4 to 7 degrees centigrade, so even more than today. And the rates that the IPCC forecasts have not been seen since then. So if we look into the early Holocene, to give you a bit of an idea of how the world looked like then, this is Europe, this is the UK here, this is Scandinavia, and you see a rather big ice sheet. 2,000 years later, it's almost gone. And this removal of this ice led to about sea level rise of about 2 meters, which is not that much, but much more important for our study area was the GIA effect, so the glacial isostatic adjustment component of this removal of the ice. So what is GIA? It's a process in which the ice pushes down the mantle into the crust. Because the ice is so heavy and so thick, it pushes the earth down. And in the zone around it, the earth is pushed up. And our study area, the North Sea, which is this area here, was in a zone that was pushed up. And when the ice disappeared, Scandinavia was coming up and our area, the North Sea, was coming down. So you can imagine that when I will talk about sea level reconstruction later on in this presentation, that this GIA effect had a huge influence on the elevation of our sea level indicators that we have used, and we have to correct for it. If we go to the other side of the Atlantic for the early Holocene, you see this very big ice sheet over eastern Canada. And then at the end of the early Holocene, only a few domes remained. And this added about 30 meters of sea level equivalent to the oceans. So, as said, if we want to improve on our forecasting capabilities for the future, we have to learn from the past, but we have to have paleo records that are of sufficient detail, especially from periods like the early Holocene, which can act as important analogs. But we didn't know enough about the early Holocene at all, in terms of sea level changes. And I would like to illustrate that with this figure here, which shows you 3 well-used sea level curves for the early Holocene. So this is the early Holocene in the red rectangle. Here is time, and here is relative sea level rise. So we have the curves of I6G from Peltier, the paleomist from Gowen, and the annual model from Lembeck. And you see that in the early Holocene, the earliest early Holocene, so around 12,000, that there's 15 meter, a range of 15 meter of sea level rise within these 3 models. So it's about plus or minus 1 Greenland ice sheet, which is, of course, a very big uncertainty. And then at the end of the Holocene, the uncertainty band or the spread in the curves is still quite big. So why do we not know enough about sea level in the early Holocene? That, of course, has to do with a lack of data. And there is a lot of sea level data. Many people around the world are working on sea level reconstructions. But if we look at this curve, this picture here on the top left that I zoom in on a little bit, you see here time and here the frequency of data points, that before 9,000, the number of data points dramatically drop as a result of the fact that this data from the early Holocene is mostly lying offshore, because sea level was so low at the time that most of these areas where they formed the indicators are now offshore. So therefore, it's really costly and very time-consuming to gather them. So most people rely on coral data, which I will talk about a little bit later on, but there's a lot of uncertainty associated with coral data, because most coral species have a living range on the water of a couple of meters at least, and therefore the uncertainty is quite big. Peat layers are used, offshore drowned peat layers, but there was no continuous record yet, and therefore the uncertainty was also quite high. So before I continue with the rest of the paper explaining that part, I'd like to take a step back and look at sea level indicators in the first place. So how do we reconstruct sea level when you look at a certain indicator? Because you have to have an indicator to tell something about the past. And I just like to show you a couple of examples. So here you see a raised beach from California. So this is the old marine terrace, or the current marine terrace, but all these flat areas here are older marine terraces, meaning that this area was uplifted. So there was a relative sea level drop here. But if you date these terraces through, and so you know how old these are, you can make a sea level reconstruction. You can plot the elevation of the terraces and the age, and then you can construct a sea level curve. Other indicators are things like these notches. So when waves attack a rock or a cliff, then a notch will form in the end. And if you find a notch at a certain place well above sea level or below sea level, it tells you a lot about past sea level if you know the age of the notch, of course. Roman fish tanks are also used. So during the Roman time, about 2,000 years ago, they had fish tanks that were open to the ocean partly, so fresh water could come in. So fresh seawater, I mean, with that. And in those tanks, the fish lived. But now you see many of those tanks underwater, meaning sea level rise. And finally, the corals that I talked about already. You have many species that you can use for that. Of course, people are looking for species that have quite a narrow living range. So for instance, if you find a coral layer at 100 meters depth that is normally living 5 meters deep, then you know that there was 95 meter of sea level change. So for my study area in the Netherlands, we often use drowned peat layers. So this example here, you see peat layers in a salt marsh setting at different elevations, with also some ages attached to it based on radiocarbon dating. And if you have a depth and you have an age, you can reconstruct sea level from these drowned peat layers. The thing, though, with those peat layers is that they all have a different relationship with sea level. So for relating a sea level indicator to past sea levels, we use a concept called the indicative meaning. And that is basically just a relationship of the water level at which this indicator formed and past sea level. So it consists of an indicative range. So that's the range over which the indicator occurs at present. So for instance, a salt marsh peat that forms in the intertidal zone, then the intertidal zone is the indicative range. And then you only have to know the intertidal range in terms of values. And then the reference water level is the midpoint of the indicative range. So in this list here, you see a lot of different types of peat that we have used for the North Sea. And here you see our indicative meanings. So for instance, this fan peat that you see here, we find it at a certain elevation, and then we say it formed in the past at 30 centimeters below mean high water. So the only thing that you then need to know is the mean high water level for that time period. I will talk about that later. And then you can say something about the water level at which the peat formed, and then also, in this case, about sea level. You also see that for the same peat type, we also use sometimes groundwater level minus 30 centimeters. And then we don't call it a slip, which means a sea level index point. So that's a peat layer that we can really relate to past sea levels. But now we call it a upper limiting data point. So sometimes you cannot relate the peat formation exactly to past sea levels, but you know then, in that case, that sea level was lower than the water level at which the peat formed, and then you use it as an upper limiting data point. And to illustrate that a little bit more, I show you this general sequence from the Western Netherlands with a Pleistocene sandy substrate. And what we find in the Netherlands a lot is a thing that we call basal peat. So in front of sea level rise, everything was terrestrial in the Netherlands and also in the North Sea. But as sea level rose, groundwater started to rise and peat started to form on a very large scale. And therefore, peat started to form. But the base of the peat, if we now find it and we date it, then the water level that controlled the start of the peat was still quite high above sea level from that time, because the shoreline was still quite far away. So if we date the base of the peat, we often say we cannot directly link it to past sea levels, but we link it to groundwater levels. So we use it at the upper limiting data point. Sea level must have been lower. But the top of the peat is different because in this sequence here, it's overlain by tidal deposits. So we know that the transition from this peat to the overlying clayey tidal deposits marks sea level quite accurately, because the water level at which this peat formed was controlled by water level in this tidal basin and hence by sea level. So in most cases, we use the top as a sea level index point and the base as a upper limiting data point. So in the North Sea, we did a lot of fiber coring, as I will show you, and we find a lot of these peat sequences. So you have a terrestrial deposit, then groundwater started to rise because of rising sea levels, peat started to form. We use the base as an upper limiting data point, peat keeps on forming. Then at some point, sea level migrates, or the sea migrates into the area, turns it into a lagoon, a brackish lagoon in most cases. So you see a transition from peat formation to clay deposition. And then in the end, the full shoreline migrates through the area and you see a erosional event due to wave action, etc. So this is the ideal sequence for us: terrestrial deposit, peat layer, brackish lagoon, and then sea sediments. Now, if we go to the North Sea again, we've made some paleogeographical reconstructions for how it looked like before it got drowned by the sea. So this is in red here is the outline of the countries in Europe. So this is Denmark, here is the Netherlands, here is the UK. Here you see still some ice over Scandinavia. So this is 13,000 years ago. And this area here, the North Sea, is called Doggerland when it is dry, was still quite a big area. And 9,000 years ago, it was already almost gone, with some islands here remaining. So this area turned into a big swamp as sea level rose, and in that swamp, peat formed, and now we can study it by coring all the peat layers in the North Sea at different elevations. So the map here on the left shows you again the North Sea with the bathymetric map in the background, but now you see all our data points. So in black, the squares are our new data points. All the lines are geophysical data lines. So on land, we looked in the borehole archives where peat can be found most likely. Then we go there with a ship. We do a lot of geophysical research. So with acoustic waves, we study the buildup of the subsurface and we select sites where we want to drill. And then we date that, and I will talk about that later on. But you also see all these circles here are existing data points. So we also incorporated legacy data, as we called it. So existing data to have a much bigger data set. And again here, this is our ideal sequence: terrestrial, peat layer, brackish lagoon, marine sediments. So some pictures from our fieldwork then. Here you see us on board of the NEOS vessel called the Pelagia. Here you see the geophysical equipment. So it's quite small, but it gives you information about the first 10 to 20 meters of the subsurface. And here you see our fiber coring system. It's relatively old. It's almost 50 years old, but it's still working quite well. And on board, we always opened the borehole first at one side to see if a peat sequence was in there. And if so, we drilled a couple of boreholes more at the same location to have enough material. So the next, I would like to show you this movie, if it works. It should work, normally works, yes. So we attached a GoPro to the fiber coring system. So it showed how the fiber core is going down. I don't know if you can hear the sound, but the sound is not so nice. Let's sort it up. Here you see the fiber core going into the seafloor. So it's really just by vibrating. The coring itself takes about 30 seconds. And then it is being uplifted. So what you see here is a steel case of about 5 meters. Inside, there's a PVC liner where the sediment is vibrated into. And then at the base, there's a core catcher to prevent the material from coming out. So here it is coming up again from the deep. In general, we were quite lucky with the weather, as you can see. So on board, we had to cut this 5 meter PVC tube into smaller sections for handling. You can see that here. And And then we opened it on board with this machine. So what did we do with all the boreholes? Of course, I already showed you that we did radiocarbon dating on the top and the base of the peat in most cases. The base after an upper limiting data point, the top a sea level index point. But we also did XRF scanning on all boreholes. XRF tells you a lot about the geochemistry of the sediments. And if we transition from a wetland with peat formation to a brackish lagoon, the geochemistry changes quite a bit. So this tells you exactly where the transition is from the peat to more clayey deposits, because we want to really date the transition. So how do we date it? We slice the peat into centimeter thick slices. We select macrofossils from it, so seeds from trees like Elmus, and then we send it to the radiocarbon lab. To further validate or substantiate that indeed above the peat the deposit is brackish, we also looked into the diatoms, which are algae, and they have fresh algae, fresh diatoms, fresh brackish diatoms, etc. So in most cases, we found that in the peat, there's sometimes already a diatom. It's always fresh. And then directly on top of the peats, you see the blue colors here, indicating brackish diatoms. So indeed, there's a brackish lagoonal deposit on top of the peat, and then we can use it as a sea level index point. At some places, we found on top of the peat also freshwater lake settings, and then we also used the top of the peat as an upper limiting data point. Of course, there's a lot of uncertainty involved, which I will talk about also later on. Especially with respect to the vertical position of the peat, you find it at a certain elevation now, but it has been changed by subsidence, by compaction, and I will talk about that. And horizontally, of course, most of the area comes from the radiocarbon dating part. But in the end, we have a rather big data set that you can see here. So here is time again, here is relative sea level, and all the blue boxes are our new data points, our new sea level index points, and in gray is an existing data set from the onshore. The T's that you see here are our upper limiting data points, so sea level, so the blue boxes must lie below the T's, which they do, and here you also see some lower limiting data points, so the boxes should lie in between those T's. So we have a data set from -50, it's good to remember, to about -2, and from 11 to 3000 years BP. So we now have a regional North Sea data set, and we wanted to go to a global signal, and that is not easy to do. So we had to think about it very long time, because we gathered the data, I think 7 years ago, and we've just published it this year. So it was a big process to go from regional signal to a global signal. And I will go through the steps that we took to do that. And of course, it starts with sea level data, which I already showed you a bit how we gathered them. But then we have to do a lot of GIA modeling. I introduced that a bit in the beginning when I showed you the disappearance of the Scandinavian ice sheet and how that impacted the vertical position of the North Sea. So we have to work on that quite hard. Then, so what we did, we subtracted the GIA component in our sea level data and ended up with a residual data set. So that's exclusive of this European GIA component. And from there, we did a lot of Bayesian modeling, which I will also show you, to end up with global sea level. But first, I will go into the uncertainties a bit more, especially the corrections that we applied. A big correction is the correction for the background subsidence. So we do not only have vertical land motion due to GIA, but also because of the land in general in the North Sea is subsiding, because it's a subsiding tectonic basin. So what you see here on this map is the rate of long-term tectonic or basin subsidence in our study area. And all these red circles here are our data points. And you see quite a big spread. So for instance, in this part here, you see dark brown colors. Then that means about 25 centimeters per 1,000 years. And here it's close to 0. But 25 centimeters per 1,000 years does not seem that much, but we have data points from 10,000 years old. So that means that we have to correct for 2 meters, meaning that, for instance, a peat that we find here is now 2 meters lower than it used to be when the peat formed. What we also did is in our radiocarbon calibration analysis is that we incorporated the stratigraphic sequence, because we knew that sea level was rising throughout the Holocene in our area at least. You also know that a peat that is higher up in the sequence must be younger than a peat that is deeper, at least if you are in the same area. So we used that in the calibration of our data points. So what you see here is an Oxcal data plot. It's a radiocarbon calibration program called Oxcal, with the age here, and here the position with respect to mean sea level. And you indeed see that if you go higher up, the dates become younger. But what you also see is that in light gray is the original uncertainty band around the radiocarbon date. But after taking into account the position of the data points, you see now in dark gray that the uncertainty band has become much smaller. So this was quite an important step, because the smaller the uncertainty band of the radiocarbon dates, the less uncertainty you have when calculating rates of change. A few slides ago, I showed you that the relationship between the peats and sea level was focusing on mean high water. So we used mean high water levels to reconstruct sea level. So we went from mean high water to mean sea level. But in the past, of course, mean high water changed, especially in the North Sea, because the North Sea used to be dry, and then later on it flooded, but initially it was still quite shallow. So this whole tidal system had to start up and change considerably through time. So for that, we used a paleotidal model from Wortetal from 10 years ago that gave mean high water values for all areas in the North Sea through time. So from this model, we obtained our mean high water value. We put this into a gigantic Excel sheet, which is part of the Handbook of Sea Level Research. It's a protocol for geological sea level database that was developed then. And in this sheet, that is now becoming more professional, also not only in Excel, but also with some more modern ways of keeping up with the data. You can add all the data, you can do the uncertainty calculations, etc. And there's a big website now called Holocene, where all kinds of people upload their data to have a huge global database. And you can see that here, it's called Holocene. This is all the data that is now in there. And we really want to formalize or have a standard way of reporting the data, and so that all people can use it in the same way. So all these corrections, and I showed a few of them, do they really matter? Therefore, I'd like to show you this slide already. What does it show? On the time again on the x-axis, but now the rate of sea level change. I will talk about that later on, but it's just now to indicate what do the corrections mean. So what you see here in black is our most favorite rate of sea level change calculation if you do all the corrections. And then the other lines are the same calculation, the rate of sea level change, but then if you do not correct for a certain component. So the red one, for instance, if you don't correct for this long-term tectonic subsidence, so this 2 meter of subsidence that I showed you for some parts of the basin, of course, impact substantially the rate of change. So we go from about 8.5 to over 10 millimeters per year, because you do not correct for this 2 meter. And paleotidal change in green, they all have their own effects on the final calculation. But what for us was important to see is that we do see these 2 peaks here in the rate of sea level change, which I will talk about, but you see those peaks in all other curves as well. So this means that these 2 peaks are not arising from any correction that we applied, but it's it's really in the data set. So we now have a sea level data set, and now we go to the GIA modeling part. Again, because maybe some of you are not so familiar with GIA, it's an effect coming from the weight of the ice pushing the Earth down. and in the area around it, the land is pushed up. So the North Sea was on such an area that was pushed up, and it's going down when the ice is gone, and it's still actually going down as a result of that. And you can see that on this map here. That shows you the modern rates of sea level change coming from GIA effects. And here in Scandinavia and also Canada, you see this grayish purple colors, negative rates of sea level change. So in those areas that were formerly glaciated, we now see a sea level drop still to this day. So what we did is we ran a lot of GIA models, 145 in total. Because you can play around a lot with those GA models, you can put the ice in different places, you can change the weight of the ice, you can change the mantle thickness, you can change the viscosity. So there are a lot of variables that you can play around with. So we did that, and then we compared it with our sea level data. And then we did a chi-square analysis to select the best performing GIA models. And what you see here in these 4 panels, is in the top left panel, you see the one outcome of a GIA model for 10,000 years BP. So it gives you the rate of sea level change, or not the rate, but the sea level change since 10,000 BP. These are our data set. So this model says there was 35 meters of relative sea level rise since then. Now the other 3 panels here show you the different contributions of the 3 major ice sheets to that 35 meters. So if we first look at this panel here that shows you the European ice sheet contribution to that 35 meters, you see that it's around 25 meters. So most of the rise came from the European ice sheet. But in the beginning, I already told you that the melt of the European ice sheet added about 2 meters of water only. So the remaining parts of this 25, so 23 meters, is just this GIA effect, this vertical land motion effect. So 23 meters of vertical land motion since 10,000 BP, which is, of course, quite a lot. If we look to the American contribution, North American ice sheet, 10 to 12 meters, which is still quite substantial. And then the Antarctic contribution was about 4 meters, according to this model. So we looked into the performance of all the models, and in the end, 8 models remained that fell into this 95 confidence intervals. So we have 8 models that we now have to correct our data set for GIA aspects. So basically what we did, we took the observed relative sea level in our data, that is the blue boxes here, and we subtracted the predicted European ice sheet component, so this 25-meter component. And then what you end up with is a residual signal that is only constituting of the Arctic and North American ice sheet signal. So we go from these blue boxes here to this new data set, the residual data set, and you see that it's now around 25, and it used to be around 50. So indeed, there's this 25-meter correction, which is, of course, really a lot. But we are still not there yet if we want to use the data for a global signal, because there's still another component that we have to correct for, and that is something that is called gravitational attraction. Because the ice is so heavy, as I told you, it pushes the Earth down, but it also has its own gravitational field, and therefore the water is pulled towards it. So the water around the ice sheet is relatively high, and when the ice melts, in fact, this pulling is so large that around the ice sheet, sea level will drop when this ice melts. And this gravitational pull and the waning and waxing of it has a certain pattern across the world, which we call the GIA fingerprint. So here you see the GIA fingerprint of the North American ice sheet for a certain period in time. But what you see here, if there's a lot of melt of ice here, then, for instance, 1 meter, then in this area, this dark blue or dark purple color, you will have -2 relative sea level. So sea level will drop -2 meters if an amount of 1 meter of ice will melt. So if you go further away, for instance, to Australia, you will get around 1 meter. If a total of 1 meter will melt there, But if we are here in the North Sea, you will see that we are in the center of this orange band. So around 70-75% of the melt we will get. So if 1 meter of sea level, 1 meter of ice will melt here, ice water, sea level water equivalent, then we will get about 75 centimeters. So that's the final correction that we had to do. So first, remove the GA component. We ended up with this curve. And then correcting for this gravitational attraction, we ended up at this gray curve here. So it's now at 37 meters again. So we went from 50 to 26, now at 37.7, with a rather large uncertainty band because of all these uncertainties involved. Now, what is very interesting is that we also looked into the sea level contribution from the ice sheets itself, so from ice sheet reconstruction, so completely independent from our sea level reconstruction. And if we do that based on literature studies, we see that North America added about 30 meters, Antarctica 7 or 8, and Europe 2, and this is about 40 meters, and that matches very well with our 38 meters. And that's really the first time. So in the past, this sea level rise since 11,000 was way higher, around 50 meters. So way higher than this ice sheet reconstruction, independent reconstruction, but now it aligns quite well. So I've showed you this plot before, but now I've added our new sea level curve into it. So what you see is that we fall a bit in between the upper two curves there. And it's clearly noticeable that this curve is way too low for the early Holocene. But what you also see is that if we go to younger time periods, that our curve is going above zero, indicating a sea level high stand. And there's more and more evidence that indeed this sea level high stand took place around 6,000 years ago, or 3,000 to 4,000 years ago, because of so the ice sheets were smaller than they are now. And that is, of course, quite interesting as well. And since then, the ice sheets in general have grown a bit. So how did we reconstruct ice sheet contribution to sea level change? As said, we based that on literature data. For the Antarctic ice sheet, we looked, for instance, into the paper from Petar et al. From 2022, where they did a lot of ice sheet modeling combined with field work, and they had 10 most likely scenarios for the contribution of sea level from Antarctica. So we used the 10 as most likely simulations to reconstruct sea level. And for North American ice sheet, we used data from, this data is not correct. It should be 2022, I think, as well. But there was a lot of ice sheet reconstructions through time. So we calculated volumes of ice based on the extent of these polygons. And then through time, we could calculate the change in volumes. For instance, this is a later map where you see much smaller ice sheet extents. And then, of course, also the volume has decreased quite considerably. So we had this curve. So you can also calculate rates of change from this curve. I already showed you that we had 2 peaks in our data, but now you see the full rate curve. So here, time, here the rate of change. And these peaks, they reach about values of 9 to 10 millimeters per year, a maximum. And after this peak, the rates of sea level change drop very rapidly. And around 7,000 years ago, you see already that it's very close to zero. For the last 2,000 years, you see here a reconstruction from Walker et al., which aligns quite well. So we really have to focus on this gap here. And then here you see the IPCC predictions, indeed, that rates of forecasted rates are in line with the rates that we see in the early Holocene. So these 2 peaks are, of course, interesting to understand where they came from. P2, so the youngest one, is already well known where it came from, because it's coming from all this water here, combined with the disintegration of this ice here. So around 8.2, 8.5 thousand years ago, these lakes, they suddenly drained into the Labrador Sea, probably in 2 phases, adding a lot of water to the oceans, resulting in these high rates of sea level change. It also impacted the Gulf Stream, resulting in a very cold period called the 8.2 event. The first phase, we don't know exactly where it came from, all the water. We don't think it's necessary that there's one specific source for it. It's probably just a culmination of a period of very rapid sea level rise. After the last ice age ended, temperatures rose quite rapidly. There was melt all over the place. So maybe that's just the end of the first phase of rapid melt. So to conclude, we have a new and updated sea level record from the southern North Sea. It's the first continuous record with relatively small uncertainties. The rate of change that we see is driven by the European, North American, and Arctic ice sheet. The contribution from Europe was mainly due through this GIA effect that we had to correct for. And in the end, we were able to calculate global rates of sea level rise. It's an important constraint for ice sheet volume reconstructions that are now aligning with our reconstruction as well. And I also like to see it as a validation set, for instance, for the IPCC models, but maybe also as a benchmark for predictive climate ice sea level models. And it's already interesting to think about how it can be used as a benchmark, because in the early Holocene, we saw rates of 1 meter per century maximum, while for the future, higher rates than that are predicted as well. But is that then very likely, considering the fact that in the early Holocene, there were very large ice sheets and temperatures were rising even faster than nowadays? So is it likely that in the future we see rates higher than that, even though maybe a model will predict it, but those models can be wrong, of course. So if we look into that a little bit more, I showed you that at 11,000 years ago, sea level was 38 meters lower. And at the peak of the last ice age, it was 120 meters lower. So that means an average of about 7.5 millimeters. So also lower than this 1 meter. So there's only one candidate period in which rates of sea level could have been higher than 10 millimeters per year. And that's a period called Meltwater Pulse 1A, around 14.5 thousand years ago, in which perhaps 10 to 20 meters of sea level rise occurred. And a recent paper that looked into that showed that most of the rise came from European ice sheet, probably, and the Antarctic ice sheet, with very high rates of sea level rise, much higher than 10 millimeters per year. So it is possible, it seems, within the system of climate and ice sheets that rates higher than 10 millimeters will be reached. But of course, we have to look into is the setting that we have now today similar to what was there in the around the Meltwater Pulse 1A setting or not? If we want to use, if we want to say that it is indeed possible, or that indeed 1 meter per century is already a sort of an upper limit. So thank you for your attention.